Hello everyone, I am Tuhin Mukherjee from Pennsylvania State University. I hope all of you are doing great and I feel so happy to see all of you join this AWS meeting. In my talk, I am going to talk about modeling of in-situ tempering of a martensitic steel during multi-layer additive manufacturing process. And before I start, I would like to acknowledge my co-authors, Dr. T.J. Leinart and Professor T. Debroy. In additive manufacturing process, especially in multi-layer directed energy deposition process with a laser heat source, the temperature fields vary in such a way that when we apply that process in a martensitic steel, the microstructure and properties depend on that. The high cooling rate in additive manufacturing process generally results in a martensitic structure in that kind of steel. But during the deposition of many layers, the repeated heating and cooling can change that martensitic structure to tempered martensitic structure, and that affect properties like hardness. So in this work, modeling of in-situ tempering due to repeated heating and cooling during additive manufacturing process is modeled and its effect is represented through hardness prediction. And here we use a combination of mechanistic model, that is a heat transfer and fluid flow model of the additive manufacturing process, and the kinetic of tempering. The main objective of this work to understand the in-situ tempering during the additive manufacturing process. And to do that, here we studied the H13 tool steel system. As you can see here, the critical cooling rate for martensite formation in this H13 tool steel is very low because it's a martensitic steel. And in additive manufacturing, you can see the cooling rates are very high, like 10 to the power 2, 10 to the power 3 Kelvin per second, in that order of magnitude. So at such high cooling rates, martensites form in H13 tool steel system. But while depositing multiple layers, because of the repeated heating and cooling, the martensites break into ferrite and carbides, and that significantly affects the hardness and spatiotemporal variation. So here the main objective is to study the effect of in-situ tempering through the prediction of hardness. And to do that, we use 3D transient heat transfer and fluid flow model of additive manufacturing process that essentially calculates the thermal cycles, the temperature distributions, and a kinetic model based on Johnson-Mehl-Abraham equation that will capture the kinetic of tempering of martensite. So the process, directed energy deposition process, has many process variables. So these process variables and alloy properties, we take both of them, and then the model can calculate the temperature and velocity fields and its 3D distribution with time, from which we can extract the thermal cycle. On the other hand, from the isothermal aging data of H13 tool steel, we can predict the constants in JMA equations. And then when we know the constants in JMA equation, we can use them over the thermal cycle to predict the hardness, through which we can understand the in-situ tempering during additive manufacturing process. So the heat transfer fluid flow model essentially solves the conservation equation of mass, momentum, and energy, and it takes input as process variables and alloy properties and provides us the transient temperature and velocity fields in 3D and thermal cycles. And as you know, the additive manufacturing, the solution domain here consists of the substrate, the deposited layer, the surrounding shielding gas, and the loose powders that are being deposited on the top of the substrate to form the layer. And the entire solution domain in that model, we discretize them into small cubes or parallelepipeds, and we solve these three equations of conservation in that domain. So for a typical solution domain, we have around 250,000 such cells like cubes or parallelepipeds, and we solve five main variables, three components of velocities and pressure to know the velocity distribution, and the enthalpy from which we calculate the temperature field. And that means for the entire solution domain, we solve about 1.25 million algebraic equations. And we need to iterate to get a good converged solution. And let's say you are doing 100 iterations per each time step. So essentially at each time step, we need to solve 0.125 billion equations. And to represent a continuous process, let's say you have 1000 time step, that means to do this calculation, you are essentially solving 125 billion equations. And how long does it take? In an inexpensive laptop, you can do that in 10 minutes. After 10 minutes, you will get all the things that you need, the 3D, transient temperature, velocity fields, thermal cycles at any locations. I can give you one example of that. This animation shows the 3D transient temperature distribution during additive manufacturing process. Here in this animation, half of the solution domain is shown because of the symmetry of the deposit with respect to XZ plane, that is the longitudinal plane. The temperature values corresponding to the contours can be read from the legend shown in the animation. You can see the temperature fields are compressed near the front edge of the molten pool, and they are expanded near the rear edge of the molten pool. And you can see the temperature fields are expanded opposite to the scanning direction because of the high scanning speed associated to additive manufacturing along the positive x-axis. So from this animation, you can see during additive manufacturing how the temperature field can vary spatially as well as with time. In this animation also, you can see the temperature field and its spatial and temporal variation during the deposition of four layers. As you can see also, the temperature field are expanded along the negative direction of the scanning. You can see that as many layers are deposited during the additive manufacturing process, the temperature fields vary significantly. Like you can see from the first layer to the fourth layer, the temperature fields are expanded as the laser beam moves far from the substrate, which makes the heat conduction from the molten pool through the substrate difficult. That accumulates more heat in the system and the temperature fields are expanded. So the bottom line from the animation is during the additive manufacturing process, while depositing many layers, the temperature fields vary in such a way that affect the microstructure and evolution of properties like hardness and their spatiotemporal variations. When we look closely to the molten pool, we can see the fluid flow inside the molten pool, and that flow are represented by black vectors as you can see in this picture. So near the center of the molten pool, the temperature is high, and towards the periphery of the molten pool, we can see less temperature, which is generally the liquidus temperature of the alloy. So the molten metal flows from the high temperature region where surface tension is low to the low temperature region where surface tension is high. So essentially that fluid flow is driven by the spatial gradient of surface tension on the top surface of the molten pool. So you can see that the black vectors are originating from the center and they are going towards the periphery of the molten pool. And on the longitudinal section, you can see the two loops representing the flow of the molten metal. And this flow of molten metal inside the molten pool mixes the hot and cold liquid and significantly affect the temperature distribution and thus the thermal cycle. So the calculated deposit shape and size, we have compared it with experiment of a steel deposit, and we can see from here that the calculated result agrees reasonably well with the experiment. So it gives us the confidence that we can use this model to accurately calculate the thermal cycle, temperature field, and use that to predict the hardness in the additively manufactured components to study the in-situ tempering. So here you can see the temperature distribution in the longitudinal section where the laser beam is at the mid length of the deposit. And this figure shows the temperature distribution during the deposition of first layer. So you can see at the first layer, inside the layer deposit, there is a monitoring location called A shown by the small white dot. And how the temperature at that particular location will vary during the deposition of subsequent layers, that is the objective of this slide. So while depositing the second layer, you can see the temperature experienced by the same location, that location is in layer 1, the temperature decreases. As we move far and deposit the third layer, the temperature at that location will even decrease, and during the deposition of fourth layer, the temperature will decrease further. So as we see during the deposition process, how temperature varies at that location, we can see it's a repeated heating and cooling. So during the first layer, deposition of the first layer, the temperature is the highest and it subsequently decreases while depositing the upper layers. So one thing is very interesting to see here, that the rate of heating is very fast, but it cools down gradually, and the rate of cooling essentially determined by the heat transfer from the molten pool through the substrate. So it cools down faster during the deposition of first layer. As it moves up, heat transfer will become more difficult as the laser beam moves far from the substrate, which reduces the rate of heat conduction. So you can see the cooling will become slow. But the bottom line here is the repeated thermal cycle, repeated heating and cooling during the deposition of many layers during additive manufacturing, noted at the same location, can significantly affect the evolution of microstructure and properties. For example, the thermal cycle recorded at the substrate deposit interface at mid length, as you can see in the left hand side schematic, the thermal cycle monitored experimentally using thermocouple at that location. When we compare that with our calculated result, we can see it agrees reasonably well. And this agreement provides us the confidence that we can use that transient temperature data during deposition of multiple layers. As example we show here for 5 layers, we can use those results to calculate the hardness. So the hardness changes as the same location experiences multiple thermal cycles. For example, the hardness, as you can see in the table, after deposition of layer 1 at location A, which is essentially in layer 1, the hardness is the highest, and that hardness is actually contributed by the formation of martensite due to very high cooling rate in DED process. And when the second layer is deposited, the reheating and recooling of the first layer will decompose some of the martensite into tempered martensite that has ferrite and carbide. So hardness drops. Hardness will eventually drop more as we deposit the third layer and fourth layer, because the reheating and recooling during the deposition of third layer and fourth layer will transform more martensite into ferrite and carbides. So hardness at the same location can decrease as it experiences more number of thermal cycles during deposition of multiple layers. And instead of looking at only at layer 1, if we look at all the layers, how hardness varies, we can see the same observation. For layer 1, after depositing the layer 1, the hardness is highest. Same thing can be observed for layer 2, layer 3 and layer 4, where the hardness is maximum after depositing second layer, third layer and fourth layer respectively. But at all locations, at each layers, the hardness decreases as is experienced more number of thermal cycles. As you see, layer 1, the hardness drops while depositing first, second, third and fourth layer. Same thing you can see for the second layer, third layer and the fourth layer. But fourth layer experiences only one thermal cycle, that is during the deposition of fourth layer. So it experiences only one thermal cycle. That's why at the end of the deposition process, that means after the deposition of fourth layer, the hardness in the fourth layer is the maximum. And hardness in the first layer, since it experiences 4 repeated thermal cycles, the hardness is the least. So you can see in a component made by additive manufacturing, multi-layer additive manufacturing, the hardness drops as we go from the top to the substrate. The hardness also significantly affected by the heat input. So here we have a plot of hardness variation with heat input per unit length, which is essentially the laser power divided by scanning speed. At high heat input, we can observe the peak temperature is high. And that high temperature essentially transforms more martensite into ferrites and carbides, and that reduces the hardness. So the hardness decreases with an increase in heat input, as you can see in the figure. To conclude this work, we can see that in this work, hardness of a additively manufactured H13 tool steel component can be correctly predicted as a function of different process variables. And the hardness in a particular location of the component continues to decrease with the intensity, duration, and number of repeated thermal cycle. A particular location, when it experiences more thermal cycle, the hardness will drop. And that is because the martensite that forms because of the high cooling rate that decomposes into ferrites and carbides due to the repeated heating and cooling. And the lower layers in the component, as it experience more number of thermal cycle, the hardness is less compared to the upper layers. And a high heat input that increases the temperature and also transform more martensite into ferrite and carbide. Subsequently, that will reduce the hardness more. So, in a future perspective, I can say that since this work shows that the hardness, a simple property like hardness and its spatiotemporal variation could be predicted as a function of different process variables. So this is a starting point that can help in future to control both microstructure and properties of additively manufactured component. Thank you. I hope you all will have a wonderful day and stay safe.